So let's keep on talking about the methodology for reduction. So yesterday we spent a lot of time to talk about if we want to get a sample reaction states from some reactors. So what kind of reactors do we need to use or include in the sampling? So and then suppose we get this issue done, and now we focus on the next step. So which is do the model reduction, right? Suppose we get a whole big set of sample states, and each state has a reaction condition with temperature, pressure, species concentrations. Then we can think of what methodology can we use to figure out for this local condition who is important and who is not important. This is a difficult question, you know. If you have a society or a coupled network, so if you want to find a subset of this network to see you guys are important and you are not important, I guess this will get a lot of people offended, right? So we need to be very careful in defining who is important. We have to make sure the definition is pairwise, so that we can see A is important to B or B is important to C. So that's a lot more reasonable. And then we can see if we are interested in figuring out what happens to species A, then who must be retained in the network. So this is a lot easier to accept. All right. So and this is what we are going to do in skeletal reduction. So skeletal reduction, if you look at this word, is to get a subset of species and reaction from a larger one. So this subset, it still functions as if it is in the larger mechanism. So their concentrations, their timescales are all similar as the detailed model. Well, whether this is possible or not, so we have to have some methodologies to check, right? So here are some of the previous methods people have been using to find those so-called important species. Let's see. So we talked about those some of the methods briefly yesterday. So and we know one of the most important one is called global sensitivity analysis, right? This is some approach always working. We get many different versions for global sensitivity. The major difference is with what sequence do you try the species? Trial and error. You need to try this one first, that one next. How to determine the sequence? That pretty much it distinguishes between different methodologies for GSA. Okay, and all this method, as long as you need to do sensitivity analysis, is time-consuming in general. Okay, if we want to do it more efficiently, there are other approaches developed before. So in the next, we will focus on one of the approach we developed about 10 years ago. It's called a directed relation graph DRG method. Okay, the DRG method is one of the example approach for skeletal reduction with a very important property that you can specify what error you can tolerate in the beginning. So before you do the reduction, you say I can tolerate, let's say, 20% worst case error. So the method should guarantee you the error is controlled, bounded. So this way, if the error is controlled, you don't have to do the validation. But you can still choose a few cases to test it, to make ourselves feel comfortable, but it's optional. But otherwise, if you cannot bound the worst case error, you do need to perform the validation for all the possible cases. So that's the difference. All right. So let's look at the concept for DRG. So DRG, basically, it starts from what I said to define some quantity to quantify the coupling between the pair of species. Let's say species A versus species B. We want to know how important B is to A. So there are many possibilities how you define this importance, right? For example, you can define them based on some sensitivity. If you change B concentration, how much omega A will change. Or you can define it based on element flux. If you look at the flux, how much carbon is flowing from A to B. Sometimes you can even define the same based on whatever probability. So if you perturb B, somehow A get messed up. So whichever way you can define, you can end up with a scalar quantity. That this quantity tells you if this number is large, so B is important to A. Otherwise, B is not important to A, right? Of course, the most direct definition is error. If I can give you a definition for error, see, this error is relative error. If you get rid of B, how much error A will have in its reaction rate. So this is the direct definition. So starting from this error definition, let's look at this one. So if you look at RAB, let me explain a little bit what this RAB means, because it's very important. Omega, of course, are the reaction rates. So each individual reaction rate. I means ith reaction. Okay. Nu AI means how many A species are participating in ith reaction. So it's a stoichiometric coefficient for A in the ith reaction. So what this says is on the bottom, every reaction, if it's contributing to reaction rate of A, we will take the reaction rate, multiply the coefficient, and put on the bottom. And we look at which one has the largest contribution. We use that number to normalize this relative error. Okay. On the top, we put a delta BI here. So delta BI means if B species B also appears in the same reaction as A, then delta is 1. Otherwise, it's 0. So it's a delta function. In this case, on the top, we have all the reaction rates which contributes to species A, which also involve species B. Right? If you get rid of B, everybody on the top will be deleted from the mechanism. All right. So and A is whoever are important to A. So after normalization, basically RAB roughly measures the relative error induced to A reaction rate due to the elimination of B. Okay, so the concept is rather simple, and this definition is a direct definition. So there can be some slight variation rather than the maximum operator. Sometimes you can use sigma, the summations, and we find different operators have slightly different performance, and somehow this maximum operator works best for like overall it works best among the different operators. And then this is what we used so far for all different cases. And then if you look at RAB, if this number RAB is close to 1, of course B is important to A, right? If RAB is close to 0, you can see B is not important to A. So if you put RAB to a graph notation, it's like this, A go to B. So in graph theory, we have nodes and we have edges. Edges usually have direction. The arrow shows direction. So this arrow shows here is if A requires B or if A depends on B. So we have to keep B if you are interested in A. So this is like a logical notation, right? So therefore, if RAB is not small, you get an arrow or you get an edge in this graph. If you put all this kind of pairwise requirements or dependence all together, it gives you a graph like this. So, and what we need to do is we just specify who you are interested in the mechanism. For example, if you're interested in the product or the field, you put it as the so-called starting species or target or starting vertex. So starting vertex is basically, this is starting node if you want to search through a graph. So starting from here, you can find B, and then from B you can find D. So go along this path. Whoever you can find in this graph, you need to keep it. And the logic here is because if D is important to B, if you delete it, B may be messed up, right? If B is important to A, you have to keep B, otherwise A can be messed up. So therefore, you do a graph search, and this graph search has a very efficient theory established already called, you can use so-called depth-first search. And you go down a path first, and then you find each one recursively. Or you can do the so-called BFS, so breadth first search first, BFS. You use different versions of searching. You get a similar efficiency, but the results should be identical. You find all the species you can reach from the starting one. And this subset of species would form a subset, which you can call it's a skeletal model. And this skeletal model, if you look at anybody in this subset, so they are happy, right? Because everybody they need are retained in this graph. And this is the key. So therefore, for this subset, you cannot find a worst case error larger than you specify. And this is pretty much the concept for DRG. It's very simple. And also, if you look at this very simple idea, you can see the worst case error in this graph is bounded. What you can do is by comparing RAB with a small epsilon number. So if RAB is smaller than epsilon, you can see there is an edge. If it's larger, if there is not an edge. If RAB larger epsilon, there is an edge in the graph. So the graph construction based on your error tolerance. So once you specify error, you can have a graph. Once you have a graph, you can easily find who need to be retained in the skeletal model. Okay. So there's one very important concept to pay attention to is if you look at the literature, there are some similar approaches to DRG, but with slightly different definition. For example, if RAB, rather than define RAB to be relative error, you can also define RAB with similar kind of a normalized quantity, but you can define it based on, for example, sensitivity. You can see if B is sensitive to A or whatever, so sensitivity. But just to make sure this RAB defined can be related to error. There's a common trick in this reduction is people tend to think if A is if this quantity says there's some big relation from A to B, then B must be retained. But that's not the logic. If you see A goes to B with big flux, of course B is important to A, right? But otherwise, if the flux from A to B is small, the key question is whether B is not important to A or not. Because what you need to do is to eliminate species, not to retain species. You have to make sure the elimination is safe. Makes sense? Because for some cases, if you define RAB to some kind of normalized flux, let's see. If you get a big flux from A to B, of course B is important to A, right? But the key is that if RAB is small, can you conclude B is not important to A? That's the key. If you cannot see RAB is small, B is not important to A, you may end up with bad elimination, and the error can lose control. That's probably the biggest trick people tend to fall in defining whatever RAB, because there's many possibilities how you can define RAB. But when you define, make sure the logic is correct. So when you have a small RAB, you have to be able to justify B is not important to A. That's the whole thing for this graph-based method. Otherwise, the method works rather quite straightforward. Let me just drink some water. Okay, so here is a sample reduction curve for the DRG method. So basically, we can run the graph search for whatever error tolerance you specified, and then you can easily get a curve like this. So number of species retained in the model versus error tolerance specified. Okay, so you can see so this curve basically you can compute very quickly with one graph search, but just slightly modify the DFS algorithm. If you are interested, you can go back to look at our paper, how you can get the entire reduction curve with a single graph search. So and if you get this curve, you can look at this one. You see it's quite smooth. Then you can see if I need less than 20% error, then you get a reduced model with less than 1,700 species, right? If I can tolerate 40% error, you get a much smaller model. So the matter is you have to specify how much error you can tolerate. Yeah, that's the key thing. And these several other curves are, if you get a huge mechanism, you probably can try the reduction a few more times, iterate a few more times. Each time, because after reduction, you get some slightly nonlinear effect. And then this reduction curve can be slightly different from the first one. The green one is the second reduction. The curve is almost the same, but slightly different. The third time, the curvature is like this. It's still slightly different. But after 2-3 times, the reduction is converged. Then you can no longer eliminate anything through a graph method. And then you stop there, and you can try to use other method to do it. Another thing to pay attention to is using the graph theory based on the design of the method. it's very dangerous if you specify a large threshold. Let's say, what if I specify 50% error? Can I still get, if you specify 50% error, you can get a very small mechanism, right? But the whole thing, how the graph-based method works, is epsilon has to be small. Okay, small means 1%, 10%, you can see it's a small number. But 50%, you can never see it's a small number. You get some nonlinear effect, then you lose the control of the worst case error. You specify error tolerance to be 50%, you may get a factor of 2 difference, or sometimes even a factor of few due to the nonlinear effect when epsilon is large. So if you use large epsilon, so this DRG will reduce to sensitivity. You do have to validate the reduced model eventually. Okay, you can still try large numbers, but then you can no longer trust it. So the practice we did is, for DRG method, we specify small tolerance only. Let's see, 30%, that's pretty much the largest we have used. And then 20% is safe. But if you want to use this for on-the-fly reduction, you probably want to be even more conservative, use 10% error. So 10% error, we never found any issue with it. So it's always work like a charm. So the rule of thumb is 10% is always safe. If you can do some validation, 30% error, you get a 95, 99% chance it's always working. If you specify 50%, the chance is it doesn't work. Okay, 50, 60%, the method will not give you what you want. So don't be very aggressive for DRG. Try to be conservative for the DRG step. After you get the first reduced model from DRG, then you can apply other method. For example, a sensitivity to it. Okay, and this is first of all the reduction time for DRG method. How much time it takes for the reduction, and this is how many species in the reduced model. So for each reduction, if you look at the mechanism of different sizes, from DME ethylene to large biodiesel fuel, like 3,000 species, you can see the reduction time is a linear function of a number of species. So this is because the whole method for DRG is only 2 major things. The construction of the method, it only involves in computation of reaction rates. Okay, that's a linear function of a number of species, as we discussed yesterday. And then secondly, the graph search. The graph search, the computer science people did a wonderful job, or discrete mathematics people, they did a wonderful job. So graph search is a strictly linear operation in graph theory. So that's the beauty of the method. That's why we use it. As a result, the reduction method is a linear time method. Okay, the linear time, that means it's very fast. If you get a larger one, you just pay corresponding larger computation time. It's not an n squared, n cubed, or even exponential of n. But sometimes if you get exponential of n, then the game is over. So then the second one is how much error was actually measured. The worst case error measured in the DRG reduced mechanism versus the specified error tolerance. So worst case measured error versus specified tolerance. If you look at this log scale, and this dashed line is 1 to 1. So you can see for the DRG method, you did get roughly the same actual reduction error versus error tolerance. This is critical. If you don't want to do the validation after reduction, so just make sure you design a method which can control the error. Okay. So there are a whole bunch of other methodologies based on DRG. For example, you can consider this so-called error propagation along the graph path. So that will involve a little bit of the modeling, because whatever error propagation is involved, it's kind of difficult to derive exactly how a species here can affect someone else far away in the graph. So you do need to get some modeling involved. Once you get a model involved, you get a risk. So the risk is sometimes the error can be controlled. Sometimes you may not be able to control the error exactly. So once you have once you have model involved, then you do need to perform post-validation for the reduction. So therefore, if you use a lot of other methodologies, you do need to sometimes iteratively to find a viable threshold. So what a threshold will give you a reasonable output reduced mechanism. Okay, and eventually the last step we always use is so-called DRG-aided sensitivity analysis. Eventually it's a sensitivity analysis because this is the most aggressive method we used. We try every possible candidates. So if you delete it, the error is fine, then we delete it. If you delete it, error is not okay, then we keep it, just as what we did before. It's brute force, time consuming, so therefore each time we run DRGASA, we put it to the last step. It takes a couple of weeks at least to do the whole reduction. But DRG typically just takes a few seconds to do a wide range of parameter. 10,000 points is just very quickly, okay? And DRG, let me maybe one thing I want to see a little bit more is about, so the DRG aided sensitivity. So what do we use from DRG to facilitate the sensitivity analysis? Because DRG gives you some kind of relative error, right? Roughly what relative error? If you get some species ranked order 1, that tends to be important. So you can probably try not to delete those very important species. For example, if you want to delete fuel, you know you will get trouble, right? So for sensitivity analysis, you want to find some simple guidance to avoid deleting or testing some very important species. For example, the fuel, the product, some formaldehyde, CO, this kind of intermediate species. In DRG, they will tell you that the error for those species would be order 1. So if they're close to 1, you just don't bother to touch them. It will save you a lot of time. If you try it, it will tell you you cannot delete it, but it's a waste of time. So that's what we borrowed from DRG. Try to avoid those meaningless elimination. So if you design any other method for sensitivity analysis, if you can try to avoid those tests which are not necessary, that can improve the efficiency for the method, and that can help. So there are many breeds of sensitivity analysis. Each have different performance. Some are more efficient, some are less efficient. But for sensitivity analysis, there's no correct or incorrect method. They are all correct. It matters which one is more efficient, which one is less efficient. Okay. So this slide shows the so-called concept of on-the-fly reduction, or people call it dynamic adaptive chemistry, DAC. So there are a lot of work going on right now for DAC. The idea here is if you want to simulate a large flame, if you look at the flame field like this is the lifted ethylene jet flame simulated by Jackie Chen, right, and Sandia. We have shown this. I showed this in yesterday morning's 1-hour lecture. So basically, this is temperature field, and then you have a lot of other quantities you can plot. But what we did is we run DRG reduction for each pixel in this 2D snapshot, and we plotted how many species are active in the flame. If you look, so you see the red or yellow color shows there are about 15, 20 species are active in the jet core where reaction occurs. There are about 5 to 10 species are important there still in the flame zone, but into the cold flow. It's still hot, you have reaction going on. The cold flow is frozen, it's chemical frozen. There's no reaction going on here. So therefore, in different regimes, there are different set of species or reactions taking control, okay? So if you can use different skeletal model in different locations, then suppose you can save some time, right? So people work on this for the last decade or two, maybe mostly last decade. There are quite a few methodologies developed. Some are based on DRG, some based on DRG-EP, some based on PFA, so pass flux analysis. So a lot of different approaches developed. But whatever method developed, make sure, because on the fly reduction, the key thing is you cannot do post-validation on the fly. You put in the method there, and then whatever it gives you, you have to take it. If you cannot make sure the reduced model is correct there, then the simulation may go wrong. So just make sure you try to be conservative if you want to do something for on-the-fly simulation. Okay. Yes.
So you said that you have different models on the same simulation, different mechanisms on the same simulation, depending on the regime.
Right. Your question is, so we want to use different models at different locations in the simulation, right?
Yes, but how can we, like, do they use the same species? Because we need to map the species, right?
Yeah, I thought to make this quick. Let me explain a little bit, because you want to ask a little bit more details about how many species you have in the in different regimes of a flow field or a reaction set. This is one of the very tricky questions in DAC. What happens is in most DAC study, people use the same set of species and reactions everywhere, okay? Because otherwise you will have conservation issue. Mass must be conserved. The key thing is using DAC, the purpose is to save time. So typically people use implicit solver to solve everything. If you get more reacting species, you get a larger implicit core to solve. So for example, here you don't need to solve any chemistry, so it's non-stiff, right? But here you solve 5 to 10 equations implicitly in each point, and here you solve about 10 to 20. The key is if you only solve those active species with implicit method locally, it can save you some computational time. Although all the species are transported, so all the species are there, they are retained. But if the species is not reacting or not important, you don't include those species in the implicit solver. So that way you can save the computational time on the fly.
So we just like in the previous time step, we realize which species are reactive, are going to change the concentration in which node, and we move forward to the next step, and the ones that are not reactive, we just equate them.
That's a very good question. So let me repeat your question. You said locally, if we look at a set of species, we run DRG or DRGEP, we find a subset of species, we said these are important. And then next time step, what would you do, right? We still run the DRG at next step and find another set of slow species, fast or reactive species. So each step, the active species may be different in different locations. But that brought a very important question to the DAC method. What happens is, for DAC, it's based on skeletal reduction. The idea is skeletal reduction. So basically, once a species is put to frozen case, if you think it's non-reacting, then it's there. Its concentration is supposed to be frozen, right? But there's a philosophical issue for DAC, because I don't think it has been well addressed. That if you assume somebody is slow, you think it's not important, you throw it away or you freeze it locally. But sometimes slow guys can become important later. Just like slow learners, they may become important long time later. Okay, so you cannot exclude the possibility that the current slow one, it must be not important in the future. But if you freeze it, you lose the chance that it will show itself in the future. So that is a key issue to be addressed in DAC. So you have to have some kind of approach, try to get it back so it has a chance to revive in the future if it can. So right now there is no rigorous method, I think, in the literature how to avoid this scenario for DAC. So therefore DAC is still a work in progress. Yeah. Yeah, but just keep in mind the main idea I put it here is, first of all, in different flame regimes, you get a different number of reactive species, active species, okay? Secondly, if you can somehow process different species or reactions on the fly, if you treat them differently, you can possibly save a lot of time for a simulation, depending on what type of flame you have, okay? The DRG80 sensitivity. Somehow the sequence for my slides is a little bit messed up. So let me explain a little bit more. Go back to the DRG80 sensitivity. So what we did here is, if we plot number of species retained in the mechanism as a function of a threshold value, this is a reduction curve. So this is for methane air, right? For DRG method, so for whatever species with smaller than, let's say, 20% error, you can safely eliminate, right, from the mechanism. Those species, you throw them away, you don't need to validate. And those species with larger epsilon values in DRG. You know they are important. They are important. They are field, they are product, whatever. So you have to keep this. You try not to disturb these guys. If you throw any of them, you find you cannot get a converged solution. The trouble if you get a convergence issue is for the test, you need to keep the case running, right, for validation. If it runs for 2 years, you need to wait for 2 years for a result. So if you throw away some species, it won't give you a lot of trouble eventually. Once you figure out you cannot throw it away. But you need to wait for a long time until it diverges and fails. So it can make the validation issue very, very much painful. You need to just wait for unnecessary much longer time if you do it. So that's the approach we did with this. We only test this small range of guys, which you throw away, you test it. If you can throw away. But otherwise, if throw away, it won't mess up your simulation. So you can still get a converged solution as Euro. Okay, so that's how we can make the sensitivity analysis still acceptable in terms of computational time with this information. And here I want to show you some of the resulting reduced mechanism after the reduction. So for example, this is an inhabitant mechanism from Lawrence Livermore. So we used the version 2 model, which is a 561 species, and after DRG, you can go to 188. So that's about a factor of 3 reduction. Okay. After sensitivity analysis, it can go much smaller, about another factor of 2.5. So basically, go to 78 species. So much smaller. So usually with DRG, we can chop half to 2/3 of the species. With sensitivity analysis, we can get rid of almost another factor of 2 or 3. So that's roughly the error. Roughly the factor we can do for reduction with the 2 major approaches. Okay. But just keep in mind, this reduction is fast. From here to here is very fast. From here is here. Although the numbers are small, it takes a lot of time. So we use our cluster with 1,000 core to do reduction. It still takes 2 weeks. So because we need to test everything. So several thousand reaction states. So basically hundreds of autoignition cases, hundreds of PSR cases, and also sometimes you need to validate the 1D flame speed, the S-curve for 1D flame extinction, sometimes 1D non-premix flame extinction, 1D premix flame extinction. One of the recent reduction we did for jet fuel, it took us almost half year to finish the whole validation process after the sensitivity analysis. Because if you don't finish everything, you cannot make sure everything is fine. That's nature for sensitivity analysis, right? So, yeah. Okay, so the second topic for reduction is the so-called timescale-based reduction. Well, skeletal reduction, what you get from skeletal reduction is, if you have been using chemical models, chemical mechanisms, so it's very easy to use them, right? Different fields, different mechanisms, they have a similar format. You get a chemistry input file with species, element, species, and reaction list. And then you get a thermal data, you get a transport data. So skeletal model has exactly the same format as a chemical model. So therefore, you can just use them if your code is compatible to chemical. It's very easy to use skeletal model. That's why many people, when they ask us for reduced model, they ask for skeletal model. They say, I use a little bit larger model, but I don't need to change any of my code. So it's easy to use. For timescale-based reduction, it goes slightly different story. So the idea behind timescale-based reduction is that sometimes if you look at a fast species, it cannot, of course, when you have radical, it cannot be fast going to nowhere, right? It typically quickly depletes itself to a very low concentration. So then it follows somebody else. We call it a quasi-steady state species in that case. After this very short initial period, nothing looks fast. There's no very thin layers. Everything changes smoothly. So at that time, if you don't bother to use a very short time step to deal with the radical, you can use algebraic equation resulting from by assuming the quasi-steady reaches its the radical reaches the steady state species. You know, you use algebraic equation together with other major species ODEs, then you can solve the system quite accurately, except the very initial short period. Okay, that's the whole idea of time-based reduction. So there are many approaches developed for timescale-based reduction. If we look at these methodologies, QSSA, you saw this in the textbook. PEA, partial equilibrium, are classical cases in textbooks, right? But what I can tell you is QSSA is widely used. So people use this in many different reduced models in the literature. Those reduced models are actually being used by engine simulations, by whatever. A lot of people are actually using it. But if you look into the literature, very few people are actually using partial equilibrium approximations. Although they are equally classical, they are developed, proposed 100 years ago, almost altogether. Okay, it's turned out this PEA is a lot more difficult to use. It's just a more difficult problem. Sometimes, if you're not very careful to handle PEA, partial equilibrium approximation, you can easily mess up the simulation. So we will talk about the trick between these two. So this one is very easy to use, robust, accurate, and this is difficult to use. That's why very few people use it. Although if you just write down one equation, one reaction on a piece of paper, they look all both fine, right? And then there are so-called rate-controlled constraint equilibrium method. So this is developed by Professor Keck in MIT. So RCC basically assumes those fast species all go to quasi-steady state. Somehow you can solve them through solving equilibrium system. Okay, and then based on eigenanalysis, we get two major methods. One is called ILDM. So the low-dimensional manifold, this one has a lot of variations. This manifold, that manifold method, but low-dimensional manifold method is developed by Master and Pope. It's one of the classical canonical approach actually being used in a lot of turbulent flame simulations even. And then CSP method, computational singular perturbation method, that's supposed to be intrinsically it's a singular perturbation method, but it's also based on Jacobian operations with iteration. So you can get a high order accuracy from CSP method. This is by Professor Lam at Princeton. Okay, so goes to the lab, develop CSP method. This is very useful tools, at least to analyze the kinetics, to understand what happens in dynamics. Although if you want to use eigenanalysis on the fly with your simulation, you may find the overhead is a bit, sometimes it's quite high, because if you can afford eigen decomposition on the fly in your simulation, you just don't bother. You can run implicit solver with Gaussian elimination, right? So it's even more efficient than eigen decomposition. So therefore, in this sense, CSP method, people use it more often in analyzing results and to understand dynamics at different reaction pathways, how they can interact with each other. So to understand the physics. So here, let me briefly introduce to you the basic idea behind ILDM and CSP. So they are all more or less you can call eigen-based method, and they are based on Jacobian. So this, again, we bring up Jacobian matrix. I told you Jacobian is relevant to almost everything in computational chemistry. So it's indeed. So Jacobian has, because it has all the important information, all the important local information embedded in the Jacobian. Okay, so by eigen decomposition, you can find the coupled groups easily. That will give you a lot of very clear information, who is working with whom to cause what. So that's the information what we can get from eigen decomposition. Well, if you look at this ODE, suppose we are dealing with a chemistry system. Y is thermodynamic states, like temperature, species concentrations, and G is a reaction source term. Let's see G is only reaction source term. Let's see if you have ODE like this, autoignition or some other 0D system, and you look at the system, you can take the chain rule, right? You can take the chain rule of the source term. Let's say it's reaction rate. So d reaction rate over dt is what you can take the J rule. You can dg dy times dy dt. if you look at this G, this is dg dy. This source term is dy dt, right? Did you see the chain rule? If you have questions, just let me know. Let me write it because it's key, you know. dy dt is g, right? If you take the chain rule dg dt, it's equal to dg dy time dy dt. Of course, this is a matrix. This is a vector. So this matrix is our Jacobian. And this guy, if you look at this, is by definition, this is the reaction rate. Okay, so the importance for doing this is to get Jacobian involved. Once you have a Jacobian involved, you can start to decouple different reactions. So what you can do next is, let's bring this back. Not this one. Not this one either. Oh, here. So what we can do here is now, once you have a Jacobian involved, let's see, this equation all of you guys are very familiar with, right? In linear algebra class or OD class, how to solve this equation. Suppose if Jacobian is a constant matrix, then you are dealing with a linear system, right? How to solve a linear system? You can easily do similarity transformation based on eigendecomposition and to do the grouping of the variables to so-called mode, right? So here you do what you can do is you can define f equal to b times, let me see, did I miss something? Let me bring this back. So let's look at this. So you know Jacobian matrix, if you do similarity transformation, this is equal to what? You can diagonalize this theoretically, right? You put something here, which is the inverse of each other, right? So the key here is G dot matrix equal to lambda, G dot not matrix, a vector equal to lambda dot vector, right? So this is a vector. So typically looks like this. So this is definition for eigenvalue, eigenvector. You can find a vector, give you this property. This is called the eigenvector, eigenvalue, right? Or you can do this B, which is a row vector dot G from the left. If it's equal to lambda time B, let me just use this. If you can do this, you can call this B is also eigenvector. And this is called the left eigenvector. So B is left eigenvector, it's a row. A is column eigenvector, it's column, right? So if you put all this together, basically what you can all see is B dot G dot A equal to lambda. This is one of the projection you can do. And also what you can do is, A dot B is a so-called Q matrix. This Q matrix is a so-called projection matrix. All right. And the G matrix is equal to sigma lambda I times Qi. So if you get a whole bunch of eigenvectors, eigenvalues involved, there are many different ways you can decompose the Jacobian. But the most frequently used one, what you can do is you can put all the let me just move this up a little bit. If you put all this A1, A2, AN together, so we will get something like this, right? G times A1 equal to lambda 1 A1, right? Lambda 2 A1, etc. Lambda n A2 AN, okay? And this is equal to basically A1 AN times lambda 1 lambda n. Give you something like this. So basically, you can call this an A matrix. A is a lot of column eigenvectors. So A time, you can call this a diagonal matrix which contains all the eigenvalues. Well, of course, this G dot A is here. This G time A is A time lambda. Or what you can see by doing a similar thing to B, you can see B times G equal to lambda times B also by doing the same thing. Or what you can do is you can see if I do the inversion for B to the other side, this one will also tell you G equal to A times lambda times A inverse. A inverse you can also call B. Because A and B are paired of, one is called the left eigenvector, one is called the right eigenvectors. This is the whole thing you need to worry about for this notation. So in CSP, they use A and they use B, but just keep in mind they are just eigenvectors which are conjugated to each other. Well, so therefore, if you put this one, G equal to A lambda B, into this ODE, you can decompose the mode, right? Let me just bring this back. You can decompose, you can transform the ODE from this form to this form, where F is equal to this B times G. So in this way, we transform the original dependent variables to the linear combinations of a whole set of others. We call this F. This F is a linear combination for the G vector, source vector. And we call this F to be mode. The mode basically tells you it's decoupled rates. Okay? So if these guys work as a group, you call this group a mode. If that guys work with a group, that's a mode. The beauty for the mode is each mode, if it's a linear system, it evolves individually by themselves. So different modes are decoupled. So for example, if you look at this equation, if you look at any particular one, let me see what. If you look at any particular guy, so suppose you are dealing with the ith mode in this vector, and dfi equal to lambda fi. You know, the solution for this one is exponential, right? You know, this solution, the solution here, what is the solution for this one? Fi is fi 0, the initial condition, time exponential of what? Is it? So therefore it tells you this one, the mode changes exponentially with time. And the lambda is, so the lambda I define a time scale of this guy. So 1 over lambda tells you time scale, how fast it e-folds. So if lambda is positive, the guy explodes, the mode explodes. That's called an explosive mode. If lambda is negative, the mode decays. The rate goes 0. You know, if you have a quasi-steady state species, the guy has to go 0 quickly, right? So naturally, it must be related with some fast decaying mode. But if you get an explosive mixture, you must be able to observe an explosive mode. So we can look at whether you have an explosive mode in the mixture to know whether it's before or post-ignition. So there's a lot of applications by looking at the explosive mode. But in the following, in the reduction, let's focus on those negative mode, where lambda is negative. Okay, so if you get, it's weird, why it's always changed by itself. So if lambda I is negative, and also it's a large number, it's large negative number. So what does this mean? So that means this mode will decay to 0 very quickly, right? How fast is the time? It's inversely proportional to lambda I. Make sense? So therefore, in that case, if you look at two different modes, if lambda I is small or moderate number, it looks like this. The slow mode looks like this is a so-called slow mode, small lambda. But if lambda is a large negative number, it decays very quickly along this path. This is called a fast mode. So if in our simulation we are not sure, or if we are not interested in what happened within this initial short period, if we are only interested in this period, why do we bother to resolve how this fast mode changes? Okay, we just assume Fi is equal to 0, the fast mode, everywhere within this domain, right? So therefore, you get Fi is equal to 0 as an algebraic equation, and you use this algebraic equation together with the ODEs, then you can solve the whole system. Then you don't have those fast guys disturbing you. All right, this is the whole idea about the eigen approach. Well, if you go back to CSP, no, the major trouble for CSP is we cannot do this linear eigen decomposition. Why? Because Jacobian is not a constant. Jacobian is a function of species concentration, function of temperature. And those numbers are a function of time also. So therefore, Jacobian is time dependent. If you consider this, if you put in the same thing as eigen decomposition, you find your lambda would have additional term, which is a time dependent. So this extra term, let me page back a little bit. This extra term is what you get by what? So let me just do this. Okay. So you know, if you do b vector dot d g dt is b dot g. So suppose this one will give you lambda b, right? And you want to call your b dot g to be your mode, but then you cannot just move b into the time derivative because b is time dependent. So it will give you additional term, which involves db dt. db dt means as time going on, the b vector changes direction. It rotates with time. So therefore, this term, it comes from the time dependence of Jacobian. It's time dependent. But once you include this term, the lambda matrix is no longer diagonal. So that's the whole trouble for nonlinear problems. We cannot just use a single eigen decomposition to get a diagonal lambda matrix. The modes won't be that easily decoupled. Otherwise, you don't call it a nonlinear problem. Okay. The CSP method is to design an iterative approach. You do iteratively, try to make this lambda as block diagonal as possible. So the iteration suppresses those two off-diagonal blocks. So the beauty for this is then you will divide the whole mode space to two parts. One is the fast mode space, one is the slow mode space. And the fast modes must go 0 by themselves. And slow modes just evolve with time. So if you have this structure, you will know what you can get is df fast dt go 0. Oh no, no, not go 0. Not d this. It's just f fast mode go 0. Very quickly. Okay, so you still need to solve this df slow dt, which is b slow times f slow. So these are the ODE to solve, but these are algebraic equations you can use by assuming all the fast modes are exhausted. So therefore, this gives you a DAE system to solve eventually. Right. So therefore, with CSP, you can do iterative procedure, but you can still use the same concept for nonlinear, if it's even strongly nonlinear problem. Okay. But the key here is still, if you want to use this approach, iteration method in your CFD simulation, it may just be too time consuming because eigen decomposition is probably one of the most time consuming operations in linear algebra. Okay, whatever involves eigen decomposition is very time consuming. So that's why we actually don't use this procedure in real CFD simulations. Try to find a solution. But this method, again, it's used a lot to understand the dynamics. Who is fast, who is slow, and who is contributing to the fast mode, who is contributing to the slow mode. All right, that's the key. Now, so let's go back then. If we want to use some reduced model, timescale-based model, still to speed up simulation, then what can we do? We don't have a lot of options left here. So today, actually, probably probably the only widely used approach right now is the quasi-steady-state approximation. So it's kind of embarrassing to say this because we have many fancy methodologies proposed, beautiful mathematics proposed, but eventually we only end up with a single methodology, QSSA, to use eventually for timescale-based reduction. For most cases, that's actually being used in engine simulation, in 3D simulations. Okay, it's very accurate and still it's useful. So QSSA, you have all learned this from textbooks, right? The scenario here is like this. If you look at this simple toy problem, if you get a major species A, form a radical B quickly go to a product C. You know, radical lifetime is short, so I use 1/epsilon to denote the key, the rate coefficient for this reaction. So, you know, for this case, B cannot be fast going forever, right? When B reacts for a short time, then its concentration is depleted, go to very low concentration. And this reaction rate will be choked by the production rate for A. So therefore, a quasi-steady state species, if you look at its concentration with time, dBdt, so this is formation rate. 1 time A is formation rate. So minus B times 1/epsilon, that's a consumption rate, right? So if you approximate this number to be 0, that tells you the consumption rate roughly balance the formation rate for quasi-steady state species. And this kind of balance is used in all the QSS approximations today. And then with this algebraic equation, you can express the radical concentration B as a function for those major ones. But this one also tells you for a quasi-steady state species, it must stay in low concentration. Why? Because of the small number. The consumption rate, the consumption or the time scale, the depletion time scale for the radical must be short for it to become a quasi-steady state species. So in this sense, not every species in low concentration you can approximate in steady state, right? Because some species, it can just happen to be in low concentration. For example, if you get an oxygen fuel mixture, you have some leakage of nitrogen, a little bit nitrogen there in the mixture. It's not reacting. You cannot possibly assume nitrogen is a steady state, because otherwise, if you solve it, you will get a totally wrong answer, right? You will get divided by 0. So solution would be totally wrong. So small concentration is not a sufficient condition to identify a quasi-steady state species, right? But then here comes the question: how can we identify who is in quasi-steady state? Have you guys thought about this before? It's a 100-year-old assumption. We are talking about this every day in chemical kinetics. In the transition state, or activated chemical state, we assume this in steady state, we assume that in steady state. But if somebody gives you a larger mechanism, how can we know who are in concentration in quasi-steady state? Reaction rate? Production rate must be small, you mean? So you are saying if a production rate for a species is small, it should be in steady state, right? But what if it doesn't have any consumption rate? So in that case, although it's slowly being formed, but it goes nowhere, it will build up, right? In that case, it never goes steady state, and you cannot solve this equation because in that case, if this number is not a large number, you don't have a consumption rate, how can you solve the concentration of B? So, but that's a very good point, because in history, 20, 30 years ago, people have been using this criteria to identify quasi-steady species. So people use several seemingly obvious criteria. One is small concentration. We know it's not right? We immediately know it's not right. A second criteria is it must be slowly forming. So the formation rate must be small. But you know, sometimes slow formation rate, you can also have slow consumption rate. So that would not be sufficient either to identify a QS species. Just give me one more minute. I have my timer set on, so I want to run over time too much. But we have to find a sufficient condition. Sufficient condition is critical, because if we don't have a sufficient condition to identify QSS species, we may risk identifying a wrong one. If we find a wrong QSS species, the consequences can be very bad because you get a single bad QSS species in your CFD simulation, it will crash the whole thing. That's why we can't make a single error in the identification. So you must find a sufficient condition. So let's take a 15 minutes break, and then after we come back, we see what is a sufficient condition. Okay.